This episode is sponsored by Brilliant. We often worry about humanity running out of room to grow outward, and many suggest we might spread out to new worlds, but perhaps we'll spread vertically first. So we return to the Earth 2.0 series to conclude our main arc by discussing Matrioshka Worlds, planets built of many concentric, spherical shells, like layers of an onion, each its own planet or layer. We'll be drawing on many of the concepts we've already discussed, such as artificial islands, colonizing the depths of the oceans or underground, bringing life to barren deserts and tundra, and even building cities floating in the sky. We'll also be drawing on technologies we've discussed in other series, like the active support technologies of the Upward Bound series, but I thought we'd begin by reiterating a point we made back in the Arcologies and Incremental episodes, which is that you are unlikely to ever run out of space for people themselves on a planet, because our real problem is coming up with the energy to support them and a way to get rid of the heat generated in the process. Incidentally, this is going to be one of our long episodes, or longer anyway, and one of the ones where I necessarily have to reference previous topics we've covered. Appropriately, for a topic involving supersizing of a planet and uprooting the continents to hang in the sky, we've got a lot of groundwork to cover first. Then we can get to why we'd likely want to dump a black hole into the center of our planet and have worlds inside worlds where the time runs slower. There's a lot to cover, so we'll be here for a while, and this would be a good time to grab a drink and a snack. Science fiction has examples of entire planets given over to immense cities, what we call at Incremental a planet city. A few of the best known of these are Trantor, the capital of the First Galactic Empire of Isaac Asimov's Foundation series, Coruscant, the capital of the Old Republic, Galactic Empire, and New Republic in Star Wars, and Holy Terra, the capital of the Imperium of Warhammer 40k. These boast massive populations compared to modern Earth, but nowhere near what they should, almost like the authors flinch back from the true scale of such places, putting in the billions or maybe a trillion or so people. As we saw in Incremental, even a trillion is very low, especially if you're cramming people into the dreary, cramped lives such places are usually described as, and points to Chris Wright in his novel Carrion Throne for finally giving a figure of quadrillions, which would fit the scale of the world given when you do the math. That's a great book incidentally, though showing a much more grim and dark future for Earth than we'll paint today. The key concept is you do not need more space in and of itself, even for such an immense figure, nearly 1 million times our current population. If we covered the entire planet only 1 story deep in fairly modest individual apartments of 50 square meters per person, or about 500 square feet, then Earth, with a total surface area of 500 trillion square meters, would house 10 trillion people. Needless to say, if you're building the kind of immense skyscrapers we often see in such stories, a few kilometers tall, or 1,000 stories, that would give you 10 quadrillion people. In these stories, where the population is often given as 1 trillion or so, but the world is nothing but mega skyscrapers, your typical person would feel like they're wandering around a deserted warehouse, not a packed residential area. The obvious point though is that it's not people taking up all that space, it's all the agriculture they need to be fed, and in fact it's not the plants taking up all that surface area, rather it's the area the sunlight falls on. The plants spread out to soak that in. For most of our history, sunlight could be treated, like air, as something so abundant that other scarcities like decent soil, rainfall, and manpower to tend crops were what dominated the equation. For a high-tech culture, those begin to diminish in importance. Machinery begins to make it easier to irrigate soil, sow and harvest crops, and science lets us improve the fertility of soil and even modify crops to be more productive, a process that our ancestors had to do in a fairly slow and hit-or-miss fashion. There's a lot of pathways to allowing more people to survive on less land, or even removing land from the equation. Greenhouses, hydroponics, and vertical farming really let you crank out calories per acre or hectare at levels that are vastly superior, such that it really can support trillions of people on Earth in comfort and with full bellies without needing to knock over any more forests or destroy any existing ecosystems. They are, however, incredibly expensive, but better energy production and automation could make them equal to or even cheaper than traditional farming a ways down the road. That's only one pathway, of course. We could grow food up in space, as we discussed in space farming, or go more artificial, either synthesizing our food or cutting that out in favor of cybernetic or digital existences, or even live in life support tanks connected to a computer and experiencing virtual reality Matrix style, and we discussed all these topics in more detail previously. Whether we are talking about space habitats like an O'Neill cylinder or terraforming other planets, all the living space you're making really has nothing to do with feeding people or giving them enough room for their furniture once you solve two basic technological hurdles. One is abundant, reasonably clean, cheap, and renewable power, and the other is considerably improved automation, not necessarily human-level artificial intelligence, but something smart enough to automate most factories, transport and production chains, and construction so that they needed minimal human oversight. Truth be told, you only need one of these technologies to basically be a post-scarcity civilization. As an example, if robots are doing most of your mining, refining, and production, you can churn out solar panels so cheaply that it doesn't matter how durable or efficient they are. The total of all our energy demands, from fuel for cars and freight trucks to electricity for houses and factories, is about 1% of the sunlight hitting Earth. So even relatively inefficient panels, placed only on barren wastelands or roofs, is going to cover your needs with room to spare. That's hardly a breakthrough in energy technology, but it hardly matters if you've got the power you need and can rely on the supply lasting half of forever without being a burden on your ecology or economy. Of course, those robots can do their work just as well on the moon and in orbit, meaning you can beam your power down and circumvent losing any land, not needing to worry about darkness from nighttime or clouds, and not having to mess around with giant arrays of batteries or superconductors to store and move your energy to where and when you need it. The flip side is that if you haven't got the smart automation, but do have a revolutionary new power production method like fusion, then you are automatically post-scarcity because the only reason we are now is because of that non-sustainable and expensive energy issue. Just the savings on electric and gas at the personal level would result in a lot of prosperity, but folks tend to forget it's built into everything. Even food production, since the three major difficulties growing everything inside climate-controlled facilities is the cost to climate control it, the cost to provide lighting or supplemental lighting, and the material cost of building and maintaining the things. Since most of us tend to assume we'll lick one or both of these issues, energy or automation, in the next couple of generations, we try to factor it into our thinking for the future here at SFIA. It's why we often present the concept that in the future, we probably wouldn't terraform dead planets for new living space so much as disassemble them for tons of artificially constructed habitats in orbit around those worlds or wherever. We always note that a spinning habitat probably only has several meters of dirt and superstructure beneath your feet, whereas a planet has several million, making it wasteful to basically build planets like Earth, since all that valuable rock is merely generating gravity, which can be created much more efficiently. We have discussed building spherical shell worlds or other shaped like disc-world flat Earths before, and using materials like hydrogen or helium or even dark matter or black holes to generate most of that gravity, with a rocky shell around it, but it's still a lot of mass you're using. This is where we truly lead into our topic for today, because that is the big limitation here. By default, most of us would rather live on a sphere than inside a can, but in an economy of truly abundant energy and automation, your economic limitation is basically on raw mass and building material, and most folks probably would not be willing to pay 1,000,000 times as much for an acre of land to have it on a sphere instead of inside a can or ring. It takes a lot of mass to make Earth, 6 times 10 to the 24th kilograms, almost 1 trillion tons per person living here, and enough to create the equivalent of hundreds of thousands of square kilometers of living area per person as rotating habitats, a modestly small nation for every living person to call their own. And so long as you're doing a sphere with Earth gravity on its surface, it will cost you the same mass per surface area whether you're making tiny planets with black holes in the middle of them for your gravity, or converting gas giants into habitable planets. Gravity falls off as the inverse square of radius. Surface area rises with the square of radius, so the two handily cancel out. However, we keep saying surface, and of course today's topic is about mini-surfaces, spheres nested in spheres inside spheres, like a Matrioshka doll, which is where we get the name for this approach. If your planet has many layers, they each can get most of their gravity from the same place, so you are not spending as much mass per living area anymore. Build thousands of layers, each as thick as a typical rotating habitat's floor, and suddenly the mass cost is very different. There's a general feeling that even if we disassemble other worlds to make huge numbers of rotating habitats, that we wouldn't do it to Earth itself, and the same would likely be true of any planet that had been the early focus of colonization in another solar system, and with such places likely being capitals and hubs of interplanetary or even interstellar empires, the real estate is likely to be precious on them. So this is one way to go for places like Earth. Of course, this raises a ton of other problems. How do you build such a thing? Second, how would you light the lower levels, since natural sunlight is blocked? Third, what do you do with all the waste heat being produced by it? Fourth, how do you build such things incrementally as need requires? Fifth, what exactly is the point of doing whole new layers when you could just go the skyscraper, vertical farming, and arcology route? And sixth, just how big can you go? How many layers can you do? Conceptually, such an object is simple enough. I build a shell over the current surface of Earth and support it somehow. We discuss the various ways in a moment. We could also go the opposite direction, hollowing a layer out below us, and indeed it would make sense to hollow a layer out to make one or more layers above you. You are probably thinking, correctly, that if we build a layer above us, we would have lower gravity there, being further up, and if we dig stuff out below us and lift it up there, we will have less gravity here at the ground level too. Now if you're keeping your layers close and not making very many, this can be ignored. But it will be an issue if you want to make lots and lots of layers and keep the same gravity on each one of them. For additional layers, you just need to ensure that the extra mass of that new layer corresponds appropriately to its distance from the center. If we go up, say, 64 kilometers to build our next layer, that layer is 1% further out than we are and has about 2% lower gravity, so that layer would need to mass about 2% of what Earth does to compensate for that. One built twice as high up as that would be 2% further out than the original ground level, and need 4% the mass of Earth, though if we built that previous layer we can subtract its mass. It just depends on how much you care about gravity diminishing as you go up, and how much sky you want to have. You can obviously do much thinner layers and space them a lot closer too, nor do all the layers have to be at the same height as full spherical shells. Though if you don't mind things hanging right overhead, you might as well go the skyscraper route or live in a rotating habitat. An important thing to remember is that a spherical shell of mass generates no net gravity inside, not just in the dead center either, but everywhere, even right inside near the shell, so you can always ignore the levels above for calculating gravity, though emphasis on net gravity, as it's not really gone, and will start making clocks and time itself run slower on lower levels if you go big enough. More on that later. Of course they can't just hang there, something has to hold all this stuff up, right? Well, yes and no. Channel regulars already know of a concept we have called active support, and it's how we cheat when we need to keep something heavy up and normal materials won't let us do it. The first of these is the Atlas Pillar, basically a particularly massive space tower whose purpose is implied by the name. It holds the sky up. Albeit, in this case the sky is the underside of another planetary layer. This type of active support works the same as what keeps a piece of paper floating over a heat vent. Nothing rigid underneath, it just gets pushed on by hot air. See the Space Towers episode for details of the science on that. But a problem with active support is that it is active. You have to pump power into the thing to keep it going, and it will lose that power as waste heat, which is problematic even if you have near-infinite, cheap power generation. If we ever manage to make cheap superconductors, and especially if we develop a material, probably a metamaterial, that makes for good magnetic shielding, then hypothetically you could make a big rod that was closed off, no new power added or heat lost, and had ridiculously high compressive strength. Inside it's got plenty of stuff moving around, but since it isn't drawing power or losing it to heat, it would be an ideal building material for stupidly big and heavy projects, like trying to hold a continent in the air. One of our other methods is the orbital ring, which relies on standard orbital mechanics. Stuff doesn't fall down for the same reason satellites and space stations don't, or rather they always fall down as orbiting objects are constantly yanked on by gravity and dropping. They are just flying out to the side at just enough speed that they wrap around a planet, constantly falling but never hitting. If a giant hand reached out and stopped the space station, everyone floating around inside would fall to the floor, as they're not that high up, so gravity is only a little weaker. Of course, when that giant hand let go, the station would plummet down to Earth too. However, if instead of stopping the station, our giant pushed it faster instead, then it would have to go up into a higher orbit, or even escape entirely. It's moving faster than it falls now. You'd have to push down on it to keep it from flying off. What an orbital ring does is merge these. We make one ring, potentially just a long and simple metal wire, that spins around Earth, and a tube around it doing the same. We use metal so we can generate a magnetic field to keep the two from touching, but still able to push on each other, and so that we can use magnetics to push on them to speed or slow either one. We spin the inner ring up while slowing the other one down, keeping their net momentum the same as a ring of equal mass to both of them would need to stay in orbit. So long as their net momentum stays at that value, either can be moving at very different speeds, and by default, an orbital ring is one where the outside does not spin at all, or no faster than the planet below it spins, while the inner moves far faster. See the Orbital Rings episode for details, but basically, you end up with a small, fast ring sheathed inside a big, stationary ring you can walk around on, as gravity feels normal, or just a little lower since you're up higher. These can handle changes of weight on that outer sheath by just speeding up or slowing down that inner ring a bit. Incidentally, there are many ways to do this, like using a particle accelerator instead of a metal hoop, and they do not need to be circular either. They could be elliptical so one end actually touched the ground. One of the ways to make a space tower or Atlas pillar is just to take that hoop and squeeze it very narrow, so that it's basically two straight lines spinning up from the ground to the top and falling back down on the other side. These things can handle staggering amounts of weight if you're willing to invest the mass and energy into spinning it up, and you could cocoon an entire planet in a bunch of them, made wide and tilted at angles, and just layer over it with rock and water and air and presto, planetary shell. Same as the Atlas pillar, if you've got cheap superconductors and magnetic shielding, you basically only have to pay your energy bill once. But in both cases, they're not nearly as power draining as you'd expect if you have to run them with modern tech. All the interior motion is just something flying around in a vacuum, so very little energy is being lost to friction and so on. Such things always require maintenance, but that applies to every structure. Such huge projects can only be contemplated with energy abundance and very good automation, but if you have them, they are not really high-tech beyond that. They are quite sturdy and safe too, especially with those rings cocooned together in case one fails. It might seem otherwise as it's unfamiliar, but honestly it's safer and sturdier than, say, living on a thin crust of rock floating on top of a huge ball of unpredictable, molten, radioactive iron as we currently do. Also, one whose mantle tends to explode through from time to time, which is handy for making new land, but we can do better, and frankly, it's just not tidy. Our core and mantle are like keeping radioactive waste and explosives in your basement, not something a responsible civilization should do, and we'll replace it with something safer like a black hole eventually. Yes, I did say a black hole. Safety, though, does encourage us to use multiple methods, and so you'd expect to see the layer built out of an orbital ring, but also supported with Atlas pillars, and many of them for redundancy. This does raise the notion of building incrementally though, and you can do that with an Atlas pillar. Just make several of them in some area, and lay land across, like a big table. You could also have a thin orbital ring running through that, or hang that shelf down from something relying on tensile strength like a space elevator, only with much less length on the tether. You could indeed do all of the above, building a landmass of a desired size, say a large island, that hung in the air between spherical shell layers, which we'll call Babylon shells, as a nod to the Hanging Gardens of Babylon. Needless to say, you could use any of the other tricks for hanging stuff in the sky that we discussed in Cloud Cities, but this approach lets you get away with making very heavy stuff, and mobile ones too, if it's just hanging from rings, like a chandelier city, or sitting on them, though skinny Atlas pillars could let you walk the thing around like Baba Yaga's hut. I suspect you'd go both ways, above and below, for redundancy and for ease of transport, particularly as Matryoshka planets need a lot more transport than just people and our personal goods and supplies. A Babylon shelf would of course shadow whatever it was above, but you could put lights on the bottom, and of course on lower layers you need to fake your sunlight anyway. It's a handy approach as you can incrementally build many of these and expand them or lift or lower them into place on a layer you're building. Since orbital rings would be a central part of your off-world economy, anytime you build a new layer, you'll need to create a new orbital ring layer to keep access to and from the planet cheap and easy. While lower layers would presumably look the same as Earth, probably with fake suns and stars, the upper layer is likely to look like the most massive scaffolding project in history, with skeletal rings wrapping the planet and space towers rising from it for millions of giant space freighters and passenger liners to dock at probably domed cities, hanging around, literally. What you do with all that space is hard to say, because you're probably not growing food on it much. You could just farm on the various levels naturally, or have vast hydroponic complexes built inside them too, but you could get away with just importing your food from huge space farms orbiting the world further out. It will generally cost less energy to land food than grow it, also meaning it will produce less heat. And you really have no need to export your waste, since you are probably constantly adding new layers of dirt. And some of the best dirt you can get is dirt that used to be food until someone ate it, so you might just import food. Amusingly, I often complain that Ecumenopolises are falsely portrayed in fiction as inevitably being what tropes call a crapsack world, and in this case that would technically be true. One nice thing about such worlds is that unlike a rotating habitat, you don't have your sky composed of your neighbor's back lawn, but actually we can double up on our layers by living upside down if we wanted. One of the incremental build methods would be just to make a wide orbital ring like a big band around a planet. and there's nothing stopping you from using the underside to produce spin, except that a spinning ring wider than a planet would be beyond what even carbon nanotubes and graphene could handle for tensile strength. One could spin it slower and fake lower gravity, which might be fun, but you can't build giant ring worlds with any material existing in known science. That is, except if you cheat and use active support. As we discussed in the Ring Worlds episode, if you have a very massive ring that doesn't spin or does so slowly, you can have another, lighter ring just inside it, spinning around very fast, by having the massive ring push back against it. It's the same basic concept as a normal orbital ring. Such things essentially hang there and are too heavy. This is like holding them up from beneath, only in this case from above, and presumably with a magnetic field so you're not touching it. Normally this is impractical since you need a really massive outer ring to allow this around a sun, like a Niven-style ring world, but it's far easier when it's just around a planet, and you do have a ton of mass just sitting there being supported, and a spinning inner ring would actually help to brace it better and give a small continent of extra living area, though you could have several. So folks could live upside down on the underside of layers too, like some sort of hollow earth notions, though since we need to name the thing to avoid confusion, and I'd rather not dignify some of the crazier hollow earth theories by borrowing their names, we shall name these upside-down, ring-shaped small continents Antipodean bands. What other fun options do we have? Quite a few. The sky's the limit, at least if you live in lower levels. Needless to say, you could devote entire planetary surfaces to being nature preserves and parks, and you could have an actual Disney World, and there is no limitation whatsoever on how many layers you can build, except cooling the place, which is a big problem. As I mentioned, your top layer is likely to be devoted more and more to spaceports and ongoing construction as you build ever bigger, so you might not even bother keeping an atmosphere up there, particularly if you decide to build one from scratch and don't want it rotating, or it wasn't rotating originally because it was a tidally locked world, so it would have no magnetosphere helping keep the sun from stripping your atmosphere off. Matrioshka Worlds are rather ideal for tidally locked planets, which will likely be fairly common since those might often be around red dwarfs, the most numerous of stars, and would often have one side baked by the sun and the other in eternal darkness. Since heat can only be transferred by radiation in a vacuum, like space, you can just put a reflective coating on a planet and keep all that sunlight off if you want to, and artificially light your lower levels. Earth, being warm and geologically active, isn't actually the best place for making a Matryoshka world, but it's also the best place in the universe for one because it's likely to always be fairly central to a future humanity. You can get away with adding more levels to our world because it is Earth, even where doing it on other worlds might be far easier. The problem is, you can't really have very many levels if you want to light them all. Our planet's temperature is based on how much light it gets from the sun and can radiate away, and that's based on its radiating surface area. If you're doubling the light with a second layer, but that layer is only a little bigger than Earth, you've got a problem. Your planet is going to get rather hot, and each new layer, while slightly increasing the surface area to radiate from, is adding far more to this heat burden. Now that's actually okay for a classic ecumenopolis, as it's assumed you're importing your food, or growing it in optimal conditions and light spectra, and any natural habitats are basically parks, a small minority of area. It's also okay to dim things in most places, as most plants don't really need for sunlight to prosper, and a big chunk of the light we get they don't even use, or use little of it like green light or infrared, which we can't even see. But this only lets you do a handful of layers, which is still quite a lot, but after that point if you want more it needs to be in darkness. That's okay if you want vast subterranean civilization, or core dark areas, or just a lot of storage space, most kept in the dark, but building a Matryoshka world with those in mind would seem like overkill. If you just want tons of storage space or caverns, you've no need to do huge layers, and can take the approach of just building story after story of whatever height you want in a particular place, like we discussed in Dying Earth. What can we do about heat? We could build them deep in space, far from a star, where they'd already be cold. These are ideal for rogue planets. But as we mentioned, we could also just shine up the surface to reflect light away so they could walk very close to stars too, and it still doesn't let you do many more layers. Of course, we might get some new technology that violated thermodynamics, in which case these become ideal places to live, or we might be able to make wormholes, dumping heat from these worlds to some other place. It may even be possible to dump waste heat into black holes, and I did mention we'd probably want one at the center of Matrioshka Worlds in some cases, though not principally for that reason, and we'll discuss that more in colonizing black holes this summer. Barring such advances, or going the dark route, if you want many layers, you need a giant surface to radiate with, or at least a giant surface area. Heat sinks to help cool devices are generally all about maximizing surface area in a compact way, and we can, for instance, stick lots of conical spikes or obelisks on the outermost layer to increase surface area, and cover them in something reflective to infrared light, which many metals already are. That will let you squeeze out more heat, and thus more layers, but we can go further too. Such planets are likely to always be surrounded by an immense swarm of space stations, docks, and orbital habitats, what we call a planet swarm, like a Dyson swarm, only smaller and around a planet. There's likely to be constant traffic back and forth to those, and huge skinny space towers potentially rising thousands of kilometers over the outermost shell. Indeed, they might just be extensions of the Atlas pillars holding it up. And possibly we'd have tons of space elevators rising from that surface too, attaching to massive counterweight habitats or space docks or farms at their far end. All along these you could have fins, like leaves on a tree, into which heat could be moved by conduction or convection into them and then radiated away, all arranged and coated in infrared reflective materials to spew out heat to fly away or bounce off neighbors until it did. Same as we have electrical superconductors that conduct electricity too, we have thermal conductive materials that move heat well and may get a thermal superconductor one day, in which case moving heat from a lower layer to these radiating towers becomes easier. You want to maximize this surface area, so you'd probably make these towers or tethers or obelisks fractal in shape, at least for their radiating leaves. And since we're using a tree analogy, and your world would be covered in these things, potentially stretching tens or even hundreds of thousands of kilometers off into space, we shall call them fractal obelisk radiation-emitting super towers, or forest, though the ST in these forests could also be space tower or space tether, I suppose. It's actually rather amusing since the purpose of these forests is to let us generate a lot of heat by lighting lots of forests and other ecosystems on lower layers, and considering the sheer scale of these things, thin and light but immense, even the massive, kilometer-long spaceships constantly flying around and docking at them would just be like birds or bees flying around a normal forest. Now we can start doing a lot more layers, and it behooves us to space them out and up and down, as we probably don't want atmosphere running between them. Same as we mentioned in subterranean civilizations, dig down real deep, and the air pressure will rise from all those extra kilometers of air piled up. Though if you don't mind airlocks along the way, or barrier mountains, you could have big holes between layers people could walk or drive directly through. You could potentially even do the equivalent of spirals instead of concentric circles, a spherical spiral or helix with one unbroken land surface, though I suspect you'd still need to be pumping a lot of air and water back up to avoid it building up, even if you were including a lot of choke points. Of course, you might enjoy having a big waterfall between layers too, or massive columns of air rising back up as an eternal storm you could hang glide between layers on. Adding to those layers, as you go up, and as I mentioned earlier, you can maintain the same gravity on each new layer by just adding enough mass to compensate for the decreasing gravity from being further away. However, as you do this, the density of your entire planet is going to start dropping off inverse to its radius. Want a planet twice as wide, with 4 times the surface area on the top layer, and the density of that sphere needs to be half in order to maintain the same surface gravity. Earth's average density is thousands of times denser than air, so you can do a lot of layers if most of those layers are relatively thin on dirt and water and mostly air by height. However, at a certain point, if your planet is now dozens of times wider than Earth is, you will actually want those layers spaced out enough that the atmosphere over each layer thins out to a vacuum before the next layers, at least on the mainland. You might keep your Atlas pillars pressurized and make them wide with their own habitats, or include stepped tiers of Babylon shells and chandelier cities. As you go down, hollowing things out though, you will slowly slice away at your gravity. Earth's pretty dense after all. Drop that density by hollowing things out, and gravity will drop. You could pack your center with something ultra-dense like osmium, but that's hardly super abundant, so you'd either have to stop or find something stable and far denser. Cue sticking a black hole in the middle of your planet. This is also a potentially awesome way to power such a place too, as various possible means of power generation from black holes are way more efficient than even the fusion that runs our sun. We'll save discussion of this more for another day, but a quick mention for now of another unintentional side effect of putting layer after layer on is that eventually, if you do enough of them, you will end up with time dilation at the lower levels, as we discussed in mega-Earths. Clocks run slowest down at the bottom layers and fastest up at the top, and among the forests and space docks. Considering new layers are likely to be inhabited by new people, especially in a future with life extension technology, you might have some very ancient folks and civilizations hanging out in the depths of such worlds, especially if you built them big enough that you were ransacking thousands of star systems to add to your building material and made the planet so big that it qualified as a mega-Earth or Birch planet, where the sun and any Dyson swarm around it would end up instead orbiting around that Matrioshka world. Such places would likely only ever be constructed because they were the natural political and economic centers of their civilizations, but if they got big enough, they might become the physical centers of such places. And indeed, regardless that the gravity on each layer might be Earth-like, the escape velocity from such things would grow too, making it very easy to approach to bring in more materials and goods, but harder to leave, another reason for those huge forests of space towers rising far away. It's a breathtaking project in scope, but one that could be done over eons as need demanded, and one I could see us doing, since for humanity at least, Earth is a unique place, and will stay unique even if we colonize 1 million other worlds and forge 1 trillion space habitats. It's an effort that might be fueled simply by Earth maintaining its prominence as the center of future civilizations. It's something that might be pushed so far that a growing Matryoshka Earth might become a truly geocentric one, with everything literally orbiting around us. So I could see this future happening, a mini-layered Earth able to house almost endless civilization and ecosystems, a new and greater Earth, an Earth 2.0. We were discussing how you can achieve the same strength of gravity on each layer of a Matryoshka world today by carefully calculating how much mass each layer needs based on its extra distance. And if you'd like to learn how to do that on your own, I'd recommend the Forces chapter in Brilliant Science Essentials course. As is often the case on this channel, we introduce the concept and folks want to create and play with it afterward, but it helps to have a good background in science and math. Brilliant offers a lot of in-depth, fun, and interactive courses and quizzes that let you master these topics at your own pace, With that course and others, you'll gain a greater understanding of how we create such worlds, from their gravity to the active support holding them up. In addition to many great courses like that, they have fun daily challenges in math, science, and engineering to encourage you to challenge yourself every day, and an extensive online community to help you if you get stuck. If you'd like to learn more science and math, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can view all the daily problems in the archives and unlock every course. So I mentioned we'd be looking at colonizing black holes soon, as part of a new crossover trilogy with some of our other series, and we'll start that next week by looking at black hole ships, and many different approaches to using black holes to move things between stars, as part of our Generation Ships and Interstellar Colonization series. We'll follow that up with a return to the Outward Bound series to look at colonizing black holes, and to our Space Warfare series with weaponizing black holes. But before that, 2 weeks from now, we'll be returning to the Upward Bound series to look at a different approach to launching ships into space, to discuss sky platforms and other launch methods that don't start by having a rocket launch from the ground. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching and have a great week.